Now that we've talked about finding basic derivatives in a much easier way using the power rule, now we can start using some base applications. And these are things that will come up throughout the course that you want to be able to do. Now, the first of those things is finding horizontal tangents. These, of course, mean that the tangent line is horizontal. It has a zero slope. Since the derivative is the slope of a tangent line, we can figure out where we have horizontal tangents whenever the derivative's equal is zero. So if we simply do the power rule, find the derivative, solve for zero, we can identify where those pieces happen. Now, one of the really helpful things that this can do for us is it quickly identifies where maximums and minimums happen. If you imagine a graph, at the very peak or valley of a graph, you're definitely going to have a spot where the line tangent to it is horizontal. So if we can figure out where the derivative equals zero, we can figure out where maximum mins happen. So let's try that out. Given this graph here, or I should say the function x cubed minus 2x, we want to figure out where it has a horizontal tangent. So we find the derivative, we solve for zero, and that will tell us the locations, the x values, where that will occur. So the derivative by the power rule is going to be f prime of x equals 3x squared minus 2. Okay, so again, this gives me the slope of the graph anywhere, but I want to know where are the slopes, zero. So if I take my derivative, set that equal to zero and solve, I can add 2 and divide by 3, telling me that x squared must equal 2/3, and therefore the places where the x is equal to 0 will be at plus or minus the square root of 2/3. Now, looking at the graph, we can clearly see that those are the locations here, because the square root of 2/3 is, almost 1. We can definitely see those are where they happen. So we have this cubic graph who has a local maximum here at the negative radical 2/3 and a local minimum here at positive 2/3. Now, the next basic application is finding average and instantaneous rate of change. Now, average rate of change is actually something we've been doing for a while. That's just another word for just our basic idea and concept of slope, where we have 2 points, and we just figure out the change in y divided by the change in x. And it's called an average rate of change because if we look here on my blue curve, this green line is what it looks like when you make that calculation. Clearly, between the first dot and our last dot, there's a lot of different slopes and a lot of different things happening. It was both, increasing and decreasing, but on average from A to B, it changed by this amount of rise and this amount of run. So it's just an average rate of change. So to do that, again, we simply use slope, all right? So y minus y over x minus x. So our green is going to be our average rate of change. However, if we look here at the red line, we can definitely tell that we can also calculate, given the derivative, instantaneous rate of change, which is the slope instantaneously at 1 point. So this slope, obviously, the average rate of change is the old kind of way we did things with 2 points. Now in calculus, having learned derivatives, this is our new way, right? We can find slope instantaneously at one spot. Now, aside from the words and the directions, the easy giveaway to know when you're doing which one would be when calculating average rate of change, of course, we have 2 points. But when you do instantaneous rate of change, we do it at one single point. So we simply find the derivative and plug the number in. And that's what you want to keep in mind. Both are clearly rates of change, but an average rate of change has to have an interval, right? Something from A to B. So you can just kind of level out and average what happened. Whereas instantaneous, working with the derivative, only requires one. Okay, so let's try both of these out using the same function. So we'll have 2x cubed minus x plus 1, and we'll begin by looking for the average rate of change over the interval 1 to 2. Now remember, this is interval notation, so if you prefer to see it as a starting ordered pair and an ending ordered pair, the first step is to find those y values. Because of course, we know that's going from 1 to 2, but we want to figure out what the function values are to see how that changes. So what we do is we plug 2 into this function here, and if you take 2 cubed, you get 8 times 2 is 16, and 16 minus 2 plus 1 works out to be 15. So we have the ordered pair 2, 15. And then we plug 1 in, you get 2 times 1 cubed, which is just 2, and 2 minus 2 plus 1 would just give us the ordered pair 1, 2. Okay, so to begin, you can make it very much feel like an Algebra 1 problem, find those two ordered pairs. So therefore, when you want to find the average rate of change, again, it's just simply finding slope. So we take our ending y value minus where we began, and then we take our 2 minus 1. So in this case, the average rate of change of this function on the interval from 1 to 2 would be 15 minus 2 over 2 minus 1, or 13. Now let's practice finding instantaneous rate of change. And again, the obvious difference is we don't have an interval, we don't have 2 points, we just have this one spot, right, when x equals 2. So that means we have to find the derivative, which gives us the instantaneous rates of change. So for this function, by power rule, it'll be 6x squared minus 1. Remember, the derivative of the constant is 0. So all we need to do now is plug in the 2. So the value of the derivative at 2 is going to be equal to 6 times 2 squared, so 6 times 4, and then take away 1. So the instantaneous rate of change at that spot is 23. Now, the last thing we want to look at is a basic falling object model. Okay, so we're going to look at real basic models of objects that are falling in space, and we'll of course be ignoring wind resistance. Now, the one thing we want to keep in mind is that depending on how we choose to measure, whether it be feet or meters, we do have to have a little bit of a difference in our model. So the position, right, the location in space, how high off the ground the object is at t seconds, generally looks like this, where you have gravity plus your initial velocity plus your position. But again, because we could measure it in feet or could measure in meters, we have different gravity constants, okay? So just measure we got the right piece here. This whole piece here is going to be our gravity, and that will always be that same number because we're assuming we're falling on Earth, okay, neglecting air resistance. So that will always be the same. If it's feet, we're going to use a negative 16. If it's meters, we'll use a negative 4.9. Now, the rest of it will be whatever numbers they give you. And of course, v sub 0, that's going to be our initial velocity. So the velocity that starts with. It's also important to understand that some models don't have an initial velocity. You certainly could have a 0 here if your object was simply dropped off a cliff. All right, you just let it go. So sometimes your initial velocity may be 0, and that's okay. But if you throw it upward, it's going to have a positive initial velocity. If you throw it straight downward, you can actually have a negative velocity. Okay, velocity is a vector component, right? It has direction. So not only is the value telling you, its speed, but it also has direction, and that's important to keep in mind. And of course, the very last thing here, this s sub 0, this is going to be our initial position. So all objects don't always start on the ground. So clearly, if we started up on top of something or whatever, that would be your initial position, which again could be 0, just in case you start on the ground. But those are all the pieces you want to keep in mind as you do this. Now, once you have your position set up, your next step is to find the velocity, okay? And the velocity is going to be our instantaneous velocity, the rate of change of the object instantaneously any time t seconds. So that, of course, means we find the derivative. Now, we will label it v of t, but just keep in mind it is the derivative of position, okay? So we just do the power rule, and that expression will give us our velocity. It can be positive or negative, again, for direction, and whatever its number is, right, just that magnitude, that's our speed. So it's important to keep in mind, if you are asked for speed, that you take the absolute value of it. So we're right, speed is the absolute value of velocity. We want the value, but we don't want the direction, okay? We never say something is traveling negative something miles per hour. So again, make sure you put the absolute value so we just have the magnitude of it. All right, so let's try an example. We'll look at an object that's being projected upward, right, from a height of 32 feet at 16 feet per second. So the first thing I want to notice is that we're not starting on the ground, okay? We have this 32 feet. So this right here is going to be my initial height. And because it's being, thrown upward, I projected upward at 16 feet per second, that 16 is going to be my initial velocity. Okay, those are important numbers. The other thing I really want to notice, of course, is feet. Okay, so that tells me that my gravity constant needs to be that negative 16. Remember, there are two different models, and we got to know which one's which. So for this particular problem, putting all those numbers together, our position at any given time, okay, and is going to be using the feet model, and we start with our gravity, so it's going to be negative 16 times squared. We're going to add on our initial velocity because it's going upward, so it is a positive velocity, so that's going to be plus 16t. And then because we're starting at a height of 32, that's above the ground, and 0 would imply a 0 height be the ground, so we're going to have a positive 32. So now that I have position, before I answer any questions, I want to make sure I have all the tools I need. So I can quickly find the derivative using the power rule to tell me, what the rate of change and the direction we're traveling is at any given time. So by the power rule, the derivative velocity is negative 32 times time plus 16. So throughout this problem, this will give me the position of the object at any given time as well as the velocity of the object at any given time. So now that I'm at a point in time where I have all my tools, I'm ready to answer whatever question they give us. So let's try a couple. So let's find the average velocity over the time period from 0.5 to 1 as far as time. Now remember, average velocity, that means slope. When you see that average, you have to remember that's just regular old slope like we talked about earlier. Velocity is a rate of change. So this is another way of saying average rate of change. And the rate of change, right, that we're looking for velocity, that's the rate of change of position. So when it says the average velocity, this is just another fancy way of saying the average rate of change of position. Okay, and that's just making sure that we know our vocabulary. Velocity is the rate of change of position, and when you say average, that means slope. Okay, so our goal here is we're going to find our slope of position. So we're going to take the position at time 1 minus the position at time 0.5, and then divide that by the time period, 1 minus 0.5. Now, I know you may look at this and think, well, the answer is velocity, and it should be something like, feet per second, and it will be. Remember, in slope, it's a fraction. The top position, that's giving you a measurement of change in feet, and then when we divide by the time on the bottom, you get that per second. So this problem absolutely is a velocity, even though we're working with, the position function s, because we're using the slope, right? And by doing that, we're actually talking about that rate of change creating velocity. So if I go ahead and you can use a calculator or whatever and plug those numbers in, just in case you don't like using the decimals with these values, I'm going to plug 1 into this right here. And when I do plug 1 into that, you get 32. And if you plug a 0.5 into this and punch it up, you're going to get 36. Okay, so just let you know. So the way it's going to lay out is going to be this average rate of change, right? The S of 1 is 32. My position at 0.5 is 36. And the time period, 1 minus 1/2 is just going to be a positive 1/2. So when I take the 32 minus 36, get negative 4 divided by that, we're going to get a negative 8. And we're measuring our rate of change here as feet, that's the numerator, per second in the denominator. So for this object, given these conditions, from 1/2 second after it's launched upward to 1 second, on average, it was moving downward at 8 feet per second. Now for our next question, let's switch it and now find the instantaneous velocity at time equals 1. Now again, this is instantaneous rate of change. So this is where we do want to go ahead and use our formula up here that is found using the derivative to calculate what that is. So we just already know what the velocity is, so we simply plug in 1. So the velocity at 1 would be negative 32 plus 16, or negative 16 feet per second. Now lastly, let's calculate the speed at impact. Now, this is a problem that takes a couple steps, because the thing is, if I want to find speed, right, that means I need to plug a number into velocity and take the absolute value, but I can't plug a number into velocity until I know the time it happens. So I need to know when impact occurs. Now, impact means it hit the ground. That means the position's equal to 0. So my first step is to solve my position for 0 to figure out when it hits the ground. Then I'll plug that into my velocity and take its absolute value. That will tell me the speed of the object at that moment it hits the ground. Okay, so step number 1 is we're going to take our position function here, s of t, and solve it for 0. Okay, now that means we're going to take our negative 16t squared plus 16t plus 32 equals 0. If I divide both sides by negative 16, I get a much easier quadratic to solve, positive t squared minus t minus 2, and that factors to give me t minus 2 and t plus 1. Now it's important to remember that theoretically this parabola exists kind of everywhere with zeros at negative 1 and 2, but in the real life domain of this problem, a time of negative 1 doesn't make sense. So that tells me that this object is going to hit the ground at 2 seconds. Now to calculate the speed, we're going to go ahead and plug that into the velocity. So the absolute value of the velocity at 2 is going to tell us, how fast it was going at that moment without worrying about the fact that it was moving downward and negative. So when we go ahead and plug that into our function, negative 32t, double that and add 16, we're going to equal a positive 48 feet per second at impact.